Chapter 8 Common Collections. Rust Standard Library includes a number of very useful data structures called collections. Most other data types represent one specific value, but collections can contain multiple values. Unlike the built-in array and tuple types, the data these collections point to are stored on the heap, which means the amount of data does not need to be known at compile time and can grow or shrink as the program runs. Each kind of collection has different capabilities and costs, and choosing an appropriate one for your current situation is a skill you'll develop over time. In this chapter, we'll discuss 3 collections that are very often used in Rust. A vector allows you to store a variable number of values next to each other. A string is a collection of characters. We've mentioned a string type previously, but in this chapter we'll talk about it in depth. A hash map allows you to associate a value with a particular key. It's a particular implementation of the more general data structure called a map. To learn about the other kinds of collections provided by the standard library, see the documentation. We'll discuss how to create and update vectors, strings, and hash maps, as well as what makes each special. Storing lists of values with vectors. The first collection type we'll look at is vector T, also known as vector. Vectors allow you to store more than one value in a single data structure that puts all the values next to each other in memory. Vectors can only store values of the same type. They are useful when you have a list of items, such as a list of text in a file or the prices of items in a shopping cart. Creating a new vector. To create a new empty vector, we call the vec::new function as shown in listing 8-1. Listing 8-1, creating a new empty vector to hold values of type I32. Note that we added a type notation here. Because we aren't inserting any values into this vector, Rust doesn't know what kind of elements we intend to store. This is an important point. Vectors are implemented using generics. We'll cover how to use generics with your own types in Chapter 10. For now, know that the vector T type provided by the standard library can hold any type, and when a specific vector holds a specific type, the type is specified within angle brackets. In listing 8-1, we've told Rust that the vector T in the V will hold elements of the I32 type. In more realistic code, Rust can often infer the type of value you want to store once you insert values, so you rarely need to do this type of annotation. It's more common to create a vector T that has initial values, and Rust provides the VEC macro for convenience. The macro will create a new vector that holds the value you give it. Listing 8-2 creates a new vector VEC I32 that holds the values 1, 2, and 3. Listing 8-2, creating a new vector containing values. Because we've given the initial I32 values, Rust can infer the type of V is a vec I32, and the type annotation isn't necessary. Next, we'll look at how to modify a vector. Updating a vector. To create a vector and then add elements to it, we can use the push method as shown in listing 8-3. Listing 8-3, using the push method to add values to a vector. As with any variable, if we want to be able to change its value, we need to make it mutable using the mute keyword, as discussed in Chapter 3. The numbers we place inside are all type I32, and Rust infers this from the data, so we don't need the vec I32 annotation. Dropping a vector drops its elements. Like any other struct, a vector is freed when it goes out of scope, as annotated in listing 8-4. Listing 8-4 showing where the vector and its elements are dropped. When the vector gets dropped, all of its contents are also dropped, meaning those integers it holds will be cleaned up. This may seem like a straightforward point, but it can get a bit more complicated when you start to introduce references to the elements of vector. Let's tackle that next. Reading elements of vectors. Now that you know how to create, update, and destroy vectors, knowing how to read their contents is a good next step. There are two ways to reference a value stored in a vector. In the examples we've annotated the types of the values that are returned from these functions for clarity. Listing 8-5 shows both methods of assessing a value in a vector, either with indexing syntax or get method. Listing 8-5 using indexing syntax or the get method to access an item in a vector. Note two details here. First, we use the index value of 2 to get the third element. Vectors are indexed by number, starting at 0. Second, the two ways to get the third element are by using the and the I'm not sure exactly, forgot what those are called, which gives us a reference, or by using the get method with the index passed as an argument, which gives us an option and t. Rust has two ways to reference an element, so you can choose how the program behaves when you try to use an index value that the vector doesn't have an element for. As an example, let's see what a program will do if it has a vector that holds 5 elements and then tries to access an element at the index 100 as shown in listing 8-6. Listing 8-6, attempting to access the element at index 100 in a vector containing 5 elements. When we run this code, the first, I guess those are just brackets, method will cause the program to panic because it references a non-existent element. This method is best used when you want your program to crash if there's an attempt to access an element past the end of the vector. When the get method is passed an index that is outside the vector, it returns none without panicking. You would use this method if accessing an element beyond the range of a vector happens occasionally under normal circumstances. Your code will then have logic to handle having either some and element or none, as discussed in Chapter 6. For example, the index could be coming from a person entering a number. If they accidentally enter a number that's too large and the program gets a none value, you could tell the user how many items are in the current vector and give them another chance to enter a valid value. That would be more user-friendly than crashing the program due to a typo. When the program has a valid reference, the borrow checker enforces the ownership and borrowing rule, covered in Chapter 4. To ensure this reference and any other references to the contents of the vector remain valid. Recall the rule that states you can't have multiple mutable and immutable references in the same scope. That rule applies to listing 8-7, where we hold an immutable reference to the first element in a vector and try to add an element to the end, which won't work. Listing 8-7, attempting to add an element to a vector while holding a reference to an item. Compiling this code will result in an error. The code listing 8-7 might look like it should work. Why should a reference to the first element care about what changes at the end of a vector? This error is due to the way the vectors work. Adding a new element to the end of a vector might require allocating new memory and copying the old element to the new space. If there isn't enough room to put all the elements next to each other where the vector currently is, in that case the reference to the first element would be pointing to deallocated memory. The borrowing rules prevent programs from ending up in that situation. Note, for more on implementation details of the vector T type, see the Nomicon at, and we've got a URL, iterating over the values in a vector. If we want to access each element in a vector in turn, we can iterate through all of the elements rather than use indices to access one at a time. Listing 8-8 shows how to use a for loop to get immutable references to each element in a vector of an I32 values and print them. Listing 8-8, printing each element in a vector by iterating over the elements using a for loop. We can also iterate over mutable references to each element in a mutable vector in order to make changes to all the elements. The for loop in listing 8-9 will add 50 to each element. Listing 8-9, iterating over mutable references to elements in a vector. To change the value that the mutable reference refers to, we have to use the dereference operator to get the value in I before we can use the plus equals operator. We'll talk more about the deference operator in the following the pointer to the value with a deference operator section in chapter 15. Using an enum to store multiple types. At the beginning of the chapter we said that vectors can only store values that are the same type. This can be inconvenient. There are definitely use cases for needing to store a list of items of different types. Fortunately, the variants of an enum are defined under the same enum type. So when we need to store elements of different types in a vector, we can define and use an enum. For example, say we want to get values from a row in a spreadsheet in which some of the columns in the row contain integers, some floating point numbers, and some strings. We can define an enum whose variants will hold the different value types. And then all the enum variants will be considered the same type, that of the enum. When we create a vector that holds the enum and so ultimately holds different types, we've demonstrated this in listing 8-10. Listing 8-10, defining an enum to store values in different types in one vector. Rust needs to know what types will be in the vector at compile time, so it knows exactly how much memory on the heap it will be needed to store each element. A secondary advantage is that we can be explicit about the types that are allowed in the vector. If Rust allowed a vector to hold any type, there would be a chance that one or more of the types would cause errors with the operators operations performed on the elements of the vector. Using an enum plus a match expression means that Rust will ensure at compile time that every possible case is handled, as discussed in Chapter 6. When you're writing a program, if you don't know the exhaustive set of types the program will get at runtime to store a vector, the enum technique won't work. Instead, you can use a trait object, which we'll cover in Chapter 17. Now that we've discussed some of the most common ways to use vector, be sure to review the API documentation for all the useful methods defined on vector T by the standard library. For example, in addition to push and pop method, removes and returns the last element. Let's move on to the next collection type, string. Storing UTF-8 encoded text with strings. We've talked about strings in Chapter 4, but we'll look at them in more depth now. New Rustaceans commonly get stuck on strings for a combination of three reasons. Rust propensity for exposing possible errors, strings being a more complicated data structure that many programmers give them credit for, and UTF-8. These factors combine in a way that can be difficult when you're coming from other programming languages. It's useful to discuss strings in the context of collections because strings are implemented as a collection of bytes, plus some methods to provide useful functionality when those bytes are interpreted as text. In this section, we'll talk about the operations on string that every collection type has, such as creating, updating, and reading. We'll also discuss ways in which string is different from other collections, namely how indexing into a string is complicated by the differences between how people and computers interpret string data. What is a string? We'll first define what we mean by the term string. Rust has only one string type in the core language. This is the string slice str that is usually seen in its borrowed form and str. In Chapter 4, we talked about string slices, which are references to some UTF-8 encoded string data stored elsewhere. String literals, for example, are stored on the program's binary and are therefore string slices. The string type, which is provided by Rust Standard Area Library rather than coded into core language, is a growable, mutable, owned UTF-8 encoded string type. When Rustaceans refer to strings in Rust, they usually mean the string and the string slice and str types, not just one of those types. Although this section is largely about string, both types are used heavily in Rust Standard Library, and both string and string slices are UTF-8 encoded. Rust Standard Library also includes a number of other string types such as OS stringing, OSSTR, C-string, and CSTR. Library crates can provide even more options for storing string data. See how those names all end up in string or str. They refer to owned and borrowed variants. Just like the string and the str types you've seen previously, these string types can store text in different encodings or be represented in memory in a different way. For example, we won't discuss other string types in this chapter. See the API documentation for more about how to use them and when each is appropriate. Creating a new string. Many of the same operations with vector t are also available with string as well, starting with the new function to create a string shown in listing 8-11. Listing 8-11, creating a new empty string. This line creates a new empty string called s, which we can then load data into. Often we'll have some initial data that we want to start with the string with. For that we use the to_string method, which is available on any type that implements the display trait, as stringing literals do. Listing 8-12 shows two examples. Listing 8-12 using the to_string method to create a string from a string literal. This code creates a string containing initial contents. We can also use the function string : from to create a string from a string literal. The code in listing 8-13 is equivalent to the code from listing 8-12 that uses to_string. Listing 8-13 using the string : from function to create a string from a string literal. Because strings are used for so many things, we can use many different generic APIs for strings, providing us with a lot of options. Some of them can seem redundant, but they all have their place. In this case, string : from and the to_string do the same thing. So which you choose is a matter of style. Remember that strings are UTF-8 encoded, so we can include any property encoded data in them, as shown in listing 8-14. Listing 8-14, storing greetings in different languages in strings. All of these are valid string values. Updating a string. A string can grow in size and its contents can change, just like the contents of vector t. If you push more data into it, in addition, you can conveniently use the plus operator or the format exclamation mark macro to concatenate string values. Appending to a string with push_str and push. We can grow a string by using the push_str method to append a string slice, as shown in listing 8-15. Listing 8-15, appending a string slice to a string using a push_str method. After these two lines, S will contain foobar. The push_str method takes the string slice because we don't necessarily want to take ownership of the parameter. For example, the code in listing 8-16 shows that it would be unfortunate if we weren't able to use the S2 after appending its contents to S1. Listing 8-16, using a stringing slice after appending its contents to a string. If the push_str method took ownership of S2, we wouldn't be able to print its value on the last line. However, this code works as we'd expect. The push method takes a single character as a parameter and adds it to the string. Listing 8-17 shows code that adds a letter / to a string using the push method. Listing 8-17, adding one character to a string value using push. As a result of this code, S will contain LOL. Concatenation with the plus operator or the format exclamation mark macro. Often you'll want to combine two existing strings. One way to use the plus operator is shown in listing 8-18. Listing 8-18, using the plus operator to combine two string values into one string value. The string S3 will contain hello world. As a result of this code, the reason S1 is no longer valid after the addition, and the reason we used a reference to S2 has to do with the signature of the method that gets called when we use the plus operator. The plus operator uses the add method whose signature looks something like this. This isn't the exact signature that's in the standard library. In the standard library, add is defined using generics. Here we're looking at the signature of add with concrete types substituted for the generic ones, which is what happens when we call this method with string value. We'll discuss generics in Chapter 10. The signature gives us the clue we need to understand the tricky bits of plus operator. First, S2 has an AND, meaning that we're adding a reference of the second string to the first string because of the S parameter in the add function. We can only add a AND str to a string. We can't add two string values together. But wait, the listing of AND S2 is AND string, not AND str, specified in the second parameter to add. So why does listing 8-18 compile? The reason why we're able to use AND S2 in the call to add is that the compiler can coerce the AND string argument into the AND str. When we call the add method, Rust uses a deferrer coercion, which here turns AND S2 into an AND S2 ... We'll discuss deferring coercion in more depth in Chapter 15. Because add does not take ownership of the S parameter, S2 will still be a valid string after this operation. Second, we can see that the signature that add takes ownership of self because self does not have an AND. This means S1 in listing 8-18 will be moved into the add call and no longer be valid after that. So although let S3 equals S1 plus and S2 looks like, it will copy both strings and create a new one. This statement actually takes ownership of S1, appends a copy of the contents of S2, and then returns ownership of the result. In other words, it looks like it's making a lot of copies, but isn't. The implementation is more efficient than copying. If we need to concatenate multiple strings, the behavior of the plus operator gets unwieldy. At this point, S will be tic-tac-toe with all of the plus and the quote, double quote characters. It's difficult to see what's going on. For more complicated string combining, we can use the format exclamation mark macro. This code also sets asks to tic-tac-toe. The format exclamation mark macro works in exactly the same way as print line, but instead of printing out the output to the screen, it returns a string with the contents. The version of the code using format exclamation mark is much easier to read and doesn't take ownership of any of its parameters. Indexing into strings. In many other programming languages, accessing individual characters in a string by referencing them by index is valid. The common operation, however, if you try to access part of a string using index syntax in Rust, you'll get an error. Consider the invalid code in listing 8-19. Listing 8-19 attempting to use indexing syntax with a string. This code will result in the following error. The error and the note tell the story. Rust strings don't support indexing. But why not? To answer that question, we need to discuss how Rust stores strings in memory. Internal representation. A string is a wrapper over a vec U8. Let's look at some of our property encoded UTF-8 example strings from listing 8-14. First, this one. In this case, len will be 4, which means the vector storing the string hola is 4 bytes long. Each of the letters takes 1 byte when encoded in UTF-8. But what about the following line? Note that this string begins with the capital Cyrillic letter ZE, not the Arabic number 3. Ask how long the string is. You might say 12. However, Rust answer is 24. That's the number of bytes it takes to encode in UTF-8 because each Unicode scalar value in the string takes 2 bytes of storage. Therefore, an index to the string's bytes will not always correlate to a valid Unicode scalar value. To demonstrate, consider this invalid Rust code. What should the value answer be? Should it be 3, the first letter? When encoded in UTF-8, the first byte of 3 is 208 and the second is 151. So answer should in fact be 208, but 208 is not a valid character on its own. Returning 208 is likely not what the user intent would want if they asked for the valid character on its own. No, wait. I read that line twice. 208 is not a valid character on its own. Returning 208 is likely not what the user wanted if they asked for the first letter of the string. However, that's the only data that Rust has in byte index 0. Users generally don't want the byte value returned, even if the string contains only Latin letters. If and hello 0 were valid code that returned a byte value, it would return 104, not H. To avoid returning an unexpected value and causing bugs that might not be discovered immediately, Rust does not compile this code at all and prevents misunderstandings early in the development process. Bytes and scalar values and grapheme clusters. Grapheme clusters. Oh my. Another point about UTF-8, that there are actually three relevant ways to look at strings from Rust's perspective: as bytes, scalar values, and grapheme clusters, the closest thing to what we would call letters. If we look at the Hindi word written in the Devanagari script, it is stored as a vector of U8 values that look like this. That's 18 bytes and is how computers ultimately store this data. If we took them as Unicode scalar values, which are what Rust's character type is, those bytes would look like this. There are 6 character values here, but the 4th and the 6th are not letters. They're diacritics that don't make sense on their own. Finally, if we look at them as Grapheme clusters, we get what a person would call the 4 letters that make up the Hindi word. Rust provides different ways of interpreting the raw strings data that computers store, so each program can choose the interpretation it needs, no matter what human language the data is in. The final reason Rust doesn't allow us to use index into a string to get a character is that indexing operations are expected to always take constant time, 0, 1, but it isn't possible to guarantee that performance with a string because Rust would have to walk through the contents from the beginning to the index to determine how many valid characters there were. Slicing strings. Indexing into a string is often a bad idea because it's not clear what the return type of the string indexing operation should be. A byte value, a character, a grapheme cluster, or a string slice. Therefore, Rust asks you to be more specific if you really need to use indices to create stringing slices. To be more specific in your indexing and indices, you want a string slice rather than indexing using with a singular number. You can use brackets with a range to create a string slice containing particular bytes. Here S will be a and str that contains the first 4 bytes of the string. Earlier we mentioned that if these characters were 2 bytes, which means S will be, what would happen if we used and hello 0 through 1? The answer, Rust would panic at runtime in the same way as if an invalid index were accessed in a vector. You should use ranges to create string slices with caution because doing so can crash your program. Methods for iterating over strings. Fortunately, you can access elements in a string in other ways. If you need to perform operations on individual Unicode scalar values, the best way to do so is to use the characters method. Calling characters on separates out the return 6 values of type character, and you can iterate over the result to access each statement. This code will print the following. The bytes method returns each raw byte which might be appropriate for your domain. This code will print 18 bytes that make up this string. But be sure to remember that a valid Unicode scalar values may be made up of more than one byte. Getting Grapheme clusters from strings is complex, so this functionality is not provided by the standard library. Crates are available on crates.io if this is the functionality you need. Strings are not so simple. To summarize, strings are complicated. Different programming languages make up different choices about how to present this complexity to the programmer. Rust has chosen to make the correct handling of a string data the default behavior for all Rust programs, which means programmers have to put more thought into handling UTF-8 data up front. This trade-off exposes more of the complexity of strings than is apparent in other programming languages, but it prevents you from having to handle errors involving non-ASCII characters later in your development life cycle. Let's switch to something a bit less complex. Hash maps. Storing keys with associated values in hash maps. The last of our common collections is the hash map. The type hash map K and V stores a mapping of keys of type K to values of type V. It does this via hashing function, which determines how it places these keys and values into memory. Many programming languages support this kind of data structure, but they often use different names, such as hash, map, object, hash table, dictionary, or associative array, just to name a few. Hash maps are useful when you want to look up data not by using an index as you can with vectors, but using a key that can be of any type. For example, in a game, you could keep track of each team's score in a hash map, in which each key is a team's name and the values are each team's score. Given a team name, you can retrieve its score. We'll go over basic API of hash maps in this section, but many more goodies are hiding in the functions defined on hash map K and V by the standard library. As always, check the standard library documentation for more information. Creating a new hash map. You can create an empty hash map with new and add elements with insert. In listing 8-20, we're keeping track of the scores of two teams whose names are blue and yellow. The blue team starts with 10 points and the yellow team starts with 50. Listing 8-20, creating a hash map and inserting some keys and values. Note that we need to first use the hash map from the collections portion of standard library. Of our three common collections, this one is the least often used, so it's not included in the features brought into scope automatically in the prelude. Hash maps also have less support from the standard library. There's no built-in macro to construct them, for example. Just like vectors, hash maps store their data on the heap. This hash map has keys of type string and values of type I32. Like vectors, hash maps are homogeneous. All of the keys must have the same type, and all of the values must have the same type. Another way of constructing a hash map is by using the collect method on a vector of tuples, where each tuple consists of a key and its value. The collect method gathers data into a number of collection types, including hash map. For example, if we have the team names and initial scores in two separate vectors, we could use the zip method to create a vector of tuples where blue is paired with 10, and so forth. Then we could use the collect method to turn that vector of tuples into a hash map as shown in listing 8-21. Listing 8-21. Creating a hash map from a list of teams and a list of scores. The type annotation hash map is needed here because it's possible to collect into many different data structures, and Rust doesn't know which one you want unless you specify. For the parameters of the key and value types, however, we use underscores. The Rust can infer the types that the hash map contains based on the types of data in the vectors. Hash maps and ownership. For types that implement the copy trait like I32, the values are copied into the hash map. For owned values like string, the values will be moved and the hash map will be the owner of those values, as demonstrated in listing 8-22. Listing 8-22 showing that keys and variables are owned by the hash map once they're inserted. We aren't able to use the variables field_name and field_value after they've been moved into the hash map with the call to insert. If we insert references to values into the hash map, the values won't be moved into the hash map. The values that the references point to must be valid for at least as long as the hash map is valid. We'll talk more about these issues in the Validating References with Lifetimes section in Chapter 10. Accessing values in a hash map. We can get a value out of a hash map by providing its key to the get method as shown in listing 8-23. Listing 8-23, accessing the score for blue team stored in the hash map. Here, score will have the value that's associated with the blue team, and the result will be sum and 10. The result is wrapped in sum because get returns an option and v. If there's no value for that key in the hash map, get will return none. The program will need to handle the option in one of two ways that we covered in Chapter 6. We can iterate over each key/value pair in a hash map in a similar manner as we do with vectors using a for loop. This code will print each pair in an arbitrary order. Updating a hash map. Although the number of key values is growable, each key can only have one value associated with it at a time. When you want to change the data in a hash map, you have to decide how to handle the case when the key already has a value assigned. You could replace the old value with a new value, completely disregarding the old value. You could keep the old value and ignore the new value, only adding the new value if the key doesn't already have a value. Or you could combine the old value and the new value. Let's look at how to do each of these. Overwriting a value. If we insert a key and a value into a hash map and then insert the same key with different value, the value associated with that key will be replaced. Even though the code in listing 824 calls insert twice, the hash map will only contain one key / value pair because we're inserting the value for the blue team's key both times. Listing 8-24, replacing a value stored with a particular key. This code will print blue 25. The original value of 10 has been overwritten. Only inserting a value if the key has no value. It's common to check whether a particular key has a value, and if it doesn't, insert a value for it. Hash maps have a special API for this called entry that takes the key you want to check as a parameter. The return value of the entry method is an idiom called entry. That represents a value that might or might not exist. Let's say we want to check whether a key for the yellow team has a value associated with it. If it doesn't, we want to insert the value 50. And the same for the blue team using the entry API. The code looks like listing 8-25. Listing 8-25 using the entry method to only insert if the key does not already have a value. The or_insert method on entry is defined to return mutable reference to the value of a corresponding entry key if that key exists, and if not, inserts the parameter as the new value for this key and returns a mutable reference to the new value. This technique is much cleaner than writing the logic ourselves. In addition, plays more nicely with the borrow checker. Running the code in listing 8-25 will print yellow 50, blue 10. The first call to entry will insert the key for the yellow team with the value 50 because the yellow team doesn't have a value already. The second call to entry will not change the hash map because the blue team already has the value 10. Updating a value based on old value. Another common use case for hash maps is to look up a key's value and then update it based on the old value. For instance, listing 8-26 shows code that counts how many times each word appears in some text. We use a hash map with the words as keys and increments of value to keep track of how many times we've seen that word. If it's the first time we've seen that word, we'll first insert the value 0. Listing 8-26, counting occurrences of words using a hash map that stores words and counts. This code will print world 2, hello 1, wonderful 1. The or_insert method actually returns a mutable reference and mute v to the value for this key. Here we store that mutable reference in the count variable, so in order to assign that value we must first difference count using the asterisk. The mutable reference goes out of scope and at the end of the for loop, so all of these changes are safe and allowed by the borrowing rules. Hashing functions. By default, HashMap uses a cryptographically strong hashing function that can provide resistance to denial of service (DOS) attacks. This is not the fastest hashing algorithm available, but the trade-off for better security that comes with the drop in performance is worth it. If you profile your code and find that the default hash function is too slow for your purpose, you can switch to another function by specifying a different hasher. A hasher is a type of implements. A hasher is a type that implements the build hasher trait. We'll talk about traits and how to implement them in Chapter 10. You don't necessarily have to implement your own hasher from scratch. Crates.io has libraries shared with other Rust users that provide hashers implementing many common hashing algorithms. Summary. Vectors, strings, and hash maps will provide a large amount of functionality necessary in programs when you need to store, access, and modify data. Here are some exercises you should now be equipped to solve. Given a list of integers, use a vector to return the mean, the average value, median when sorted, the value in the middle position, and mode, the value that occurs most often. A hash map will be helpful here of the list. Convert strings to Pig Latin. The first consonant of each word is moved to the end of the word and a is added, so first becomes fray, word that starts with the vowel, and hay added to the end instead. Apple becomes apple hay. Keep in mind the details about UTF-8 encoding. Using a hash map and vectors, create a text interface to allow users to add employees' names to a department in a company. For example, add Sally to engineering or add Amir to sales, and then let users retrieve a list of all people in a department or all the people in a company by department sorted alphabetically. The standard library API documentation describes methods that vector, strings, and hash maps have that will be helpful for those exercises. We're getting into more complex programs in which operations can fail, so it's a perfect time to discuss error handling. We'll do that next.